Swayam Prabha. Digital India. Educated India.
So last class I have discussed about different types of seismic waves. So I have discussed about the body wave, surface wave, what are the different types of body wave and what are the different types of surface wave, and then what are their characteristics, what are the type of particle motion. So now this class I will discuss how we can locate the epicenter of an earthquake by using this using the seismogram data, and let's see that how the actually your waves they changes their direction when there are two different materials. Okay, so that means when seismic wave travels from one material to another material, the path of the wave is refracted. So let's discuss that. So suppose if we are taking two different cases. Okay. So first case, it is your high speed material . And this is low speed material. And in this case, this is low speed. Okay. And this is high speed. Now, if the material wave is moving like this is the direction of the wave for both the cases, and this is the vertical line or normal. So in case of first case, when it is moving from low speed to high speed, then it will move away to the normal. So if this is the actual direction, then it will move away to the normal. And in this case, when it is moving from high speed to low speed, it will move towards the normal. So this case, it will move towards the normal, and this is away from the normal. Okay. So now here, because of that, you can see that as we have mentioned that the crust density is around 27, or unit weight is around 27 kilonewton per meter cube to 30 kilonewton meter cube, whereas the mental density is more than that. It may be 35 sometimes, and it can be around 5 also. I mean 50 kilonewton per meter cube also. Thus, that means the mantle is the denser material compared to the crust. So now, if your focus is here, which is within the crust shape. So now, when the wave will release, it will release in the infinite direction. So now, when it will release, and then from here, when it will go to the mantle, so that means the mantle will be your density is more. So it's see that if your velocity of the wave is more if the material density is more. So that means your velocity increases as density increases. This is the your common pattern, common rule. So if I write down the velocity, say shear wave velocity, which is root over g by rho. Okay, so that means it is shear modulus divided by density. Now I am saying velocity increases, density increases, but it is not showing like this, because velocity is proportional to 1 by root rho. But the reason is that when your density increases, then your modulus value will also increase. So modulus value will not be constant if your density increases. So that means if your material become dense, the shear modulus value will also increase. So that's why as your density increases, then your velocity will increase. So this is the common thing that we follow. But later on I will show you that in case of earth, different layers, these things is not following. Okay, these things also depend some other factors. Okay, so that means, but right now if I see the focus, crust and the mantle, or the lower mantle, upper mantle, so it is following this way, that up to this, that your velocity increases as density increases. So that means your lower mantle has more velocity of the wave, then upper mantle has slight is velocity which is lower than the lower mantle, and crust has the velocity of the wave which is lower than the mantle. Okay, so that if you see crust, upper mantle, lower mantle, so crust has the lowest velocity and lower mantle has the highest velocity of the wave. Okay, because their density increases as we go towards the earth core. So that means when focus is on the within the crust. So now when wave travel from crust to mantle, so that means it is from low speed material to high speed material. So that means it is low speed material to your high speed material. So you can see this is low speed material to high speed material. So that means it will move away to from the normal, because you see it move away from the normal, so it will also move away from the normal. Now it will travel through the mantle, and then when it will reach the boundary between mantle and the crust, then it will be low speed material to the high speed material to the low speed material. From crust to mantle, low speed material to high speed material, this ray will move away from the normal. Now when it will reach the boundary of mantle and the crust, then it will be high speed material to the low speed material. Now this case, your wave will move towards the normal. I have discussed it will move towards the normal, second case. So in this way, it will reach to the ground surface. That means this is the refracted rays. Okay, and this, because of that, it will reach to the ground surface. Clear? Now sometimes in a single layer, if density increases with a pattern, then also if it is density increases in the one layer particular with some pattern, so in a single layer, say, density increases as depth increases, then also there will be refraction and it will reach to the ground surface. So later on I will discuss all these cases. Okay, density increases in a layer, okay, with depth, then different layer with different density, so then it will also reach to the ground surface. So this is the reason why it will reach to it may travel to the crust, it may travel from crust to mantle, then it will refract, and then it will go back to the surface also. So that means from crust to the surface it can reach, then it can reach crust, then mantle, then again crust, again to the surface. So different way it can move and move to the surface where you place your seismograph. Clear? So now these are the things that why this is moving and when it will this direction will move away from the normal, when it will be towards the normal, I have discussed. Now next one, that the two information that I want to give, that you can see if this is the source of an earthquake. Now here the earthquake that will generate S wave, P wave both, and then when S wave, P wave will reach the ground surface, then the surface wave will be developed. Okay, but this 100 up to from 0 to 103 degree, both S wave and P wave will reach to the ground surface. But from 103 to this 180, and then from this side also 103 to 180, no surface wave will be reached, because we know that our outer core liquid in nature, and surface wave cannot pass through liquid. It can pass through solid only. So that means when the surface will come here, then it cannot pass. So that means there will be no direct S wave will reach in this zone. Okay? Now you come to this part. This part also you can see there is no direct S wave zone, but there is no direct P wave zone also. So let me explain why. Because of this, that is also because of this your liquid nature of outer core. But before that, let me explain about the different velocity pattern as per depth for different waves. So now if we have, this is our earth crust, okay, and then we can go up to the inner core. So this is crust, then this is the crust and mantle boundary, this is the mantle and outer core boundary, and this is our inner core. This is crust, mantle, this is inner core, this is outer core. Yeah. So I have drawn one extra layer. Okay. So that means this is crust, this one is the mantle, this one is the outer core, and this is the inner core. Clear? Now the boundary between crust and the mantle is called moho, and boundary between mantle and the outer core is called the Gutenberg discontinuity. Okay, so but this outer core is liquid in nature, you know. Now if I draw the density pattern as for the depth, okay, this is density, which is gram per centimeter cube. So you can see that density crust is the lowest, you know, then it will increase up to the boundary of mantle and core. Then at this boundary it will suddenly increase, though it is the liquid nature of the outer core, but still at this boundary your density will increase. Then again it will more or less constant or slightly it will increase. Then at this boundary of outer core and inner core it will again increase, and then it will follow up to this around 14, and then again it will follow like this. So this is the density variation along the depth. So if this is the depth, and this is the density variation. Now the value will be around, this is 5.5 gram per cc, this is 9, this one is the 12, and this one will be around 15, okay, gram per cc. So that means the density increases as you go to the Earth's surface. So it is starts from around 3 from here at the crust, 2.7 to 3. So starts from 3 to it reaches to 15 in the inner core, which is the densest layer of the Earth. Clear? But now if I draw the wave pattern, wave velocity pattern, shear wave and your P wave, and then you will see this is the depth. So depth wise variation. So first I will draw that your shear wave. So that means it will velocity will in the crust, from crust to the mantle, velocity will increase. Then it will become 0 at the boundary between mantle and the outer core. Because outer core is a liquid in nature, so that's why the velocity will be 0, it cannot pass through the outer core. That is S wave, okay? That is S wave. Now in case of P wave, how these things will change? So again from initial part it is same, variation is same as S wave, okay? So initial part it is same as S wave, but only the different value. It is increases. Then at the boundary between mantle and the outer core, it suddenly decreases. Okay, it suddenly decreases. Then again it starts increasing again. And when in the boundary between outer core and inner core, it slight decrease, and then it will again increase, and then it will follow like this. Clear? It is kilometer per second. If I write the value, so you know that at the crust the velocity of P wave, this is P wave, which is approximately 7 kilometer per second, and the maximum is 13.5. That is at the boundary between the mantle, or you can say at the end of the lower mantle, that is 13.5. Then it will suddenly decrease, and then at the inner your inner core it is 11 kilometer per second. And as you know that S wave velocity is around 1.7 or 1.89 times lower than the P wave velocity. So on the crust is approximately 3 kilometer per second. So that means you can see that when a wave is moving from crust to mantle, then it is from low speed material to high speed material. But okay, when a wave is moving from mantle to inner core, then it will be a different thing, because your velocity at the inner core, wave velocity is lower than the mantle, though the density of the inner core or outer core is more than the density of the mantle. But the velocity of the inner or outer core is, velocity of the wave is lower than the velocity of the wave in the mantle. So that means here you can see when it will enter here, then the refraction pattern will be different. Okay, because now it will be initially when we discuss about crust to mantle, it is low speed to high speed. Now it is high speed to low speed. So because of this liquid nature of the outer core, and so then there will be a refraction wave, and then wave will not reach, this P wave will not reach in between 103 to 143. So this both side. So that means this 103 to 142, there is a zone where no direct wave will reach, either it is S wave or P wave. But the reflected wave can reach. But I am talking about the direct wave, means this refracted or direct wave. Okay. So that means here it is mentioned that direct wave will not reach. So that means from 0 to 103, P wave, S wave both will reach. from 103 to 143 no wave will reach, no direct wave will reach, but from 143 to 183 only P wave will reach, because S wave will not reach because of this inner core nature, because that is liquid and it cannot flow through liquid. Clear? So that means is what we are saying, that if the density increases, velocity of wave also increases. That when you discuss about our soil properties determination, that time we will follow this trend, because that is okay. But here at different material properties and the boundary, that will. So now, so that means there is a shadow zone, shadow P wave zone, and shadow P and S wave both zone, that is been discussed here. Now let me discuss about the locating the source of an earthquake. Locating the source of an earthquake. So first, suppose this is your site. This is your site of interest, from where I want to determine the distance from the source to that site. So this is your focus where earthquake is being generated. Okay, this is my focus. Now if I draw a perpendicular line through the focus, the place where it touches the ground surface, that is called epicenter. Okay, so this is my epicenter. So epicenter is on the ground surface, but focus is below the ground surface. Clear? This focus is sometimes called focus or hypocenter. Okay. Now if I join this site to the focus and then site to the epicenter, now distance between site of interest to the epicenter is called epicentral distance. Distance between site to the hypocenter, that is called hypocentral distance. So it is clear what is epicentral distance, what is hypocentral distance. Clear? So that means this focus or hypocenter is below ground surface and epicenter is on the ground surface. Now if I know the velocity of P wave and S wave, then distance between the seismograph or the site where you place the seismograph and the focus or hypocenter of an earthquake can be determined as this equation. This equation you can prove that it is just the distance from this d is the distance and S wave and P wave is traveling, and you know there is a arrival time between S wave and P wave. So here Bs is the velocity of the S wave and Vp is the velocity of the P wave, and del Tps is the time difference between the arrival of P wave and S wave. Okay, that you will get from the seismograph or seismogram, I think so. Seismograph is your instrument and which will produce the seismogram. So now if I know this del Tps, that means this arrival time distance, and if I know the velocity of S wave and P wave, I can determine the d. Now the question is that if I know the velocity of this P wave and S wave, that means the P wave and S wave has to pass through a particular layer of the earth, because there your velocity is constant. Or we can say that if it is passing through the crust, then the velocity of the P wave is 6 km per second and velocity of the S wave is roughly 3 km per second. So that we know. That means, what does it mean? Mean that to use this expression, one condition that your hypocenter focus should be in shallow depth. So that means this equation is applicable for shallow earthquake. Okay, this equation is applicable for shallow earthquake. So that means if the distance between epicenter and the hypocenter is very less, or say few kilometers, then we can use this expression. There your travel will, this wave will travel through the your crust only, and then that distance is very less, that depth, few kilometers, compared to the distance between hypocenter to that site or the epicenter to that site. So in that case, we are determining though the d value, which is the distance between focus and the your site, but still that we can use as a epicentral distance, because the epicentral distance and hypocentral distance will be very more or less same, or there will be very less difference, because if the depth of distance between epicenter and hypocenter is very small. So that is the condition to use this expression. Okay, so that means it is applicable for shallow earthquake. Now this is if what will happen, that if it is the deep earthquake or intermediate earthquake, then how we can determine the location of the epicenter. Okay, so now in the second method is the locating the your source of earthquake. Now if it is here deep or intermediate earthquake, but it can be used, you can use it for shallow earthquake also. Okay, you can use it for shallow earthquake also. So that means here, but here I don't know the velocity of the wave. Clear? Previous class I should have know the velocity of the wave, but here I don't know the velocity of the wave. So wave can travel, if it is a deep earthquake, it can travel through mantle, it can travel to crust. So I don't know actually. So but what I know, I have that seismogram data from this seismograph, this seismograph data, this your from data, and I have this travel time versus distance plot. So this travel time versus distance plot is available, where the distance from the epicenter to the travel time for P wave and S wave are plotted. So now if I have that, and then if you see this travel time versus distance plot, that as your distance of the site from the epicenter increases, then this difference between the travel time of P wave and S wave will also increase, or increases, or will also definitely increase, because as your distance increases, then the travel time difference between P wave and S wave, that will also increase. So that is the case. You can see for 1000 kilometer, this distance, this difference is say around 2 minutes. But for 4000 kilometers, this difference is 1, 2, 3, 4, 5, 6, around 6 minutes. Okay. So now what I will do, I will take this data and then I will fix this data on this travel time versus distance plot, and I will place it towards the left or right. I will place it toward the left or right, and I will fix it in such a way that the starting point of P wave and the starting point of S wave will meet this P wave and S wave curve respectively. So if I shift this plot left to right, definitely there will be a position where these things will happen. So I will locate that position. That position will give me the location of that site from the epicenter. Clear? So this way I can determine the epicentral distance for that particular location where this seismograph is placed. Okay. So now, but if I use one particular reading, so whether this is this method or this method, if I use one data of one particular location or one seismograph, then I will get the distance, but I will not get the direction, because one particular site there may be n direction, infinite direction, from where actually the location of earthquake I don't know, but I know the distance, but I don't know the direction. So if I draw a circle taking center as that your site, and radius will be equal to the d, or the distance from epicenter to that site, and if I draw a circle, so the earthquake location can be any point on that circle, but I don't know the which point. So to do that, what I have to do, I have to exactly locate the epicenter. I have to take the help of at least 3 seismograph data, at least 3. So that is true for here, that is true for here. So it's a second point, you may get the location that where this is the starting point of P, and this may be S, this may be the starting point of P. So this will be your second this may be the distance of the second location from the epicenter. Similar way you can get the third one also, this may be the third one. So you will get D1, D2, D3. So that means you have say 3 points, 1, 2, 3, and then you draw 3 circle. So this is say D1, then for 2 you draw another circle, this is maybe D2, and for 3 you draw another circle that will pass okay. So it will pass this point. So point where this all these 3 circle pass, then that point is the epicenter of the earthquake. Clear? So but you need at least 3 points to locate that epicenter, and that is true for here also, and here also you need the 3 data, at least 3, but if you use more than it will be good, your accuracy will be increased. Sometimes you will find that because of this some approximation, that these 3 points may not touch, but I mean this circle may not touch a single point, or they may not pass a single point. So then in that case there will be a triangle will generate. So if this circle passes not passes to a single point, so there will be a triangle will generate, a small triangle. So centroid of that small triangle will be the epicenter in such case. But if they passes through a single point, then it is okay. Otherwise, this will be centroid of that triangle will be epicenter. So this is my epicenter. Clear? So this way I can locate the epicenter of an earthquake. So I have discussed if it is a shallow earthquake, you can use this method. If for other case, you can use this method, but this is a common method that you can use for all types of earthquake. So today I am finishing my lecture here. So next class, what I will do, I will solve one example problem, and then by solving that example problem, I will try to give you an idea how you can locate the epicenter of an earthquake, and then if time permits, then I will discuss about the size of earthquake. Thank you.